The last kind of communication that we talk about in this unit is communicating energy using an enthalpy graph. So we've already used butane combustion a few times. So the butane combustion is exothermic. So if we did the combustion of butane, and it was the enthalpy of combustion of butane, it's an exothermic reaction. And so exothermic reactions start with more chemical potential energy. So we write the potential energy, EP, for chemical potential energy. And this is going to be megajoules because it was a lot of energy. And this is going to be reaction progress, maybe time, or perhaps reaction coordinates. There are lots of different possible labels we can put on the y-axis. Essentially, the reactants have a lot of chemical potential energy, and then they give off heat, and the products have less potential energy. So then I write down what the reactants are at the beginning. So 13/2 oxygen gas, and then my products are 4 carbon dioxide gas and 5 water vapor. And the enthalpy here is going to be equal to negative 2.87 megajoules, because this is still for 1 mole of the reactant. The energy is being given off, so it has more chemical potential energy in the reactants than in the products. This energy is being given off, and you can tell it's exothermic partly because we give it the negative symbol. Please note that the only time you put megajoule per mole is when you don't have the reaction written down. If I have given you the reaction, or if you're given the reaction, or if you know the reaction and it's written out, you never put per mole, because this is the megajoules for 1 mole of this, 13/2 moles of this, 4 moles of this, and 5 moles of this. So this energy applies to all of the conditions. So that's an exothermic graph, and it steps down. If we had the enthalpy of ethane cracking, which we knew we just saw in a previous video was an endothermic reaction, then I have my reactants down here, and my potential energy in, I believe it's kilojoules in this case, is down here, and we had ethane, and we had to put energy into it, and then it broke down into ethene and hydrogen gas. This is reaction coordinates. We need to have a label on our graph here, and the enthalpy of this reaction was positive 136.4 kilojoules, and that's per 1 mole of this. If we'd have doubled this value, this would have to be twice as big an amount. If I wanted to get rid of the fraction on this side by multiplying by 2, this would also get multiplied by 2. But endothermic reactions have the positive symbol for the energy, exo have the negative, and the graph for exothermic steps down, endothermic steps up. More potential energy in my reactants than my products for endothermic reactions. Exothermic reactions have more chemical potential energy in their reactants than their products. Now, we don't see these graphs too often, but you need to be able to interpret them. We're going to be adding to these graphs in chapter 12. But these graphs can help us really keep track of a lot of different factors, comparing the amount of chemical potential energy being a really important one. If I know that this is an exothermic reaction, this energy, this heat energy is being given off, and that I've got more bonds are being made than broken because the heat is being given off. Here we've got more bonds being broken than made because it took more energy. So if we can keep track of these graphs, we can keep things more straightened out. And a lot of the questions, when I'm answering them on the diploma, I like to come back to the visual on these graphs and do a double check. So if I've got that, I can just rattle through questions more quickly.